Go for it, Anna.
All right, thank you today. Thank you, Meta, for inviting me. This talk is called The Atom and the Bomb, the Discovery, Fission, and the Development of Nuclear Weapons. Oops. This is just a quick overview of the areas that I'm going to cover. The first one is sort of scientific work that laid the foundation for the development of nuclear weapons. The second part is about the Manhattan Project, with an emphasis on the experience of the scientists who were involved with that. And the third section will address the issue of nuclear weapons today and their effects. So I want to take you back to 1932. The big question in physics is, what was the nature of the atom? This is the model that physicists were using in 1932. You can see here's the nucleus in the center of the atom with electrons orbiting around it. This is more the model that we use today. We have a much more nuanced idea of where the electrons are and sort of what they might be doing. That's not useful for this talk, but I thought I should put it in case there are any scientists who are aghast at my out-of-date model. So here it is. Now, scientists knew about protons, and they knew protons were in the nucleus, but they didn't really know what else was going on in there, and they really did want to explore that. So these two men, John Cockcroft and Ernest Walton, they decided they would probe the nature of the nucleus by shooting a proton into the nucleus of a lithium atom and see what happened. It was the nature of the experiments people were doing at that time. They were always bombarding atoms with subatomic particles. So both the proton and the lithium nucleus are positively charged, and positive charges repel each other, so it's quite difficult to do this. So they had to design a new kind of generator to create an enormous voltage to be able to slam the proton into the lithium nucleus. And this is a photograph of that apparatus. Here's the proton source up here, here's the generator, and here's a little wooden observation hut with Ernest Walton inside. It was necessary because there was quite a good risk of being electrocuted, being around this equipment, and he has a screen in there that he can monitor the results of the experiment on. So what they were expecting is that when the proton hit the lithium nucleus, it would emit gamma rays. But instead, they detected helium nuclei, which are also known as alpha particles. Now, they were quite familiar with alpha particles, and they knew, because they could add up the masses, that what happened was the proton combined with the lithium and then split into two new atoms, so two atoms of a new element, helium. They had split the atom. It's more correct to say they split the nucleus. This was really exciting because they finally had a good insight to what the nucleus actually was. So that's good if you're interested in atomic structure. But they also discovered that the reaction, this nuclear reaction, produced a lot of energy. Well, energy, 11 million electron volts of energy. So what does that mean? So they got 17 million electron volts from disrupting the nucleus. Most of the reactions that happen on Earth are not nuclear, they're chemical, they involve the electrons. They will give a few electron volts per reaction. So the energy from the nucleus can be 1 million times more than the energy you get from regular chemical reactions, which was quite exciting. But if we take it into the macroscopic world where we live, 17 million electron volts is very, very little. A mosquito uses 1 billion electron volts just to fly. So, and you saw how difficult it was to get those 17 electron volts, the big apparatus, the huge voltage. So that's why, in 1933, Ernest Rutherford, who was the physicist supervising Cockcroft and Walton, he said, the energy produced by the breaking down of the atom is a very poor kind of thing. Anyone who expects a source of power from the transformation of these atoms is talking moonshine. It's interesting, actually, the way sort of public opinion has followed or in some way preceded these events. People were already aware that atoms may produce a lot of energy, and there was a lot of interest in this in the popular press at the time. But Rutherford's remark really irritated this man. His name is Leo Szilard. He was a Hungarian physicist, and he felt sure that Rutherford must be wrong. He just had to figure out how to, get at the energy within the nucleus. So the story goes, he was standing on a street corner one day in London waiting for the light to change, and it suddenly hit him. A nuclear chain reaction. So what he thought was, if you could split one atom, and then the products of that reaction could go on and split two atoms, and then the products of those reactions could go on and split four, like that, you'd be able to split as many atoms as you wanted. His second thought was, you would be able to make a really powerful bomb if you could do that. And he was so horrified at that prospect that he immediately went out and secretly patented the idea with the hope that he would be able to prevent anyone from using this technology to make a weapon. The chain reaction is quite an important concept. So I'm going to show you a film clip from a Walt Disney's film made in the 1950s called Your Friend the Atom, that talks about chain reactions in uranium. Oops.
One bullet was used to split the atom, and two new ones were created in the process. Now we have two neutrons to split two atoms. This implied a fabulous prospect, a nuclear chain reaction in uranium. Let's go back to our mousetrap atoms. We can create a chain reaction with them. We'll use our two ping pong balls for neutrons. They will be released when the atom splits. Now all these mousetraps are the atoms that will be in the game. They are set, loaded, and ready to go. To start the chain reaction, all we need is one neutron. It has to trigger just one trap. The ping pong balls that are released will set off two other traps. And then we'll have four balls flying to trigger more traps. I think you can see what is going to happen. Watch. An atomic chain reaction works in exactly the same way.
So, back to the 1930s. Szilard didn't know how to create a nuclear chain reaction. He just came up with a concept. These two scientists, Otto Hahn and Lise Meitner, they're the people who actually performed the experiment. They were working in Germany, in Berlin, in 1938. Meitner was Jewish, and she actually, before the actual experiment was performed, she had to flee to the Netherlands and eventually to Switzerland. But she was still involved in sort of the theoretical part of the work. So what they did was they took a neutron, this is a neutron, and they hit the nucleus of a uranium-235 atom. That's a particular isotope of uranium. And they split it into two smaller atoms, but they also created three neutrons. So those neutrons could go on and to then split more atoms, and that's how the chain reaction worked. We just have a really quick look at the periodic table. This is a list of all the atoms in increasing size. So here's uranium down here, 92, it's really big. And it's split into barium, which is number 56, and krypton, which is number 36. This kind of nuclear reaction where a big nucleus breaks into smaller parts is called fission. When the results of this experiment were published in December of 1938, every physicist who read that paper realized that now it would be possible for the Nazis to build an atomic bomb. So our friend Szilard swung into action. He didn't try to stop them with his patent. What he did was he wrote a letter to President Roosevelt asking him to set up an American atomic bomb project. And he got his friend and teacher, Albert Einstein, to sign the letter. At first, nothing much happened, but eventually, the Manhattan Project came into being. And it really got going after the bombing of Pearl Harbor. The task of this project was actually quite daunting. They had to take these recently discovered scientific principles and use them to build an actual weapon that would work, for sure. So, you remember the Hahn-Meitner experiment with uranium. It turns out that that reaction will happen spontaneously. And if you have enough uranium-235, it'll explode just all by itself, just because it's radioactive. Occasionally, a nucleus will break apart, it will create neutrons, and if there are enough other atoms of U-235 around it, it'll just explode. So the smallest piece of uranium that you can use to have this kind of explosion is called the critical mass. So the Manhattan Project had to find the ore, or who had the uranium ore. They had to refine it to extract the uranium. They had to figure out how to enrich what they had to get the U-235. Naturally occurring uranium is almost all uranium-238. You know, isotopes, they have different numbers of neutrons, but they're the same element. So they just differ slightly by weight. They're chemically identical. So they had to figure out how to get pure uranium-235 when what they started out with was only 0.7%. And then they had to calculate the critical mass and design a bomb that would be able to use this as an energy source. So what they did was they put two small pieces of uranium in the bomb. They're too small to be critical by themselves, but then the bomb was detonated by a small chemical explosion that would slam those two pieces of uranium together. The piece that you got would have critical mass and it would explode. Just in case that didn't work, they designed another completely different kind of bomb using not uranium, but plutonium. Plutonium does not occur naturally in nature in any substantial amounts. It was only discovered in 1940. It's the product of a nuclear reaction with the other isotope of uranium, uranium-238. If you put it in a nuclear reactor, it will transmute into plutonium. So the scientists had to figure out how to build nuclear reactors, because they'd never done that before, how to extract the plutonium, and then it turned out that plutonium is not stable enough to actually be used in a bomb like the one with uranium, because it'll sometimes spontaneously, or more easily spontaneously, start to react. So they developed this kind of bomb, which has a sphere of plutonium in the middle. And instead of adding more plutonium to reach critical mass, they would compress it so the atoms were closer together and they could achieve critical mass that way. So they had to put conventional explosives all around it and coordinate them to compress it all at once. It was rather a technical challenge. So that kind of work, you need a huge team of people and a lot of resources. And that's what the military was able to provide. The Manhattan Project had over 30 sites in the US, some in Canada and in Britain. We'll just point out a few here. University of Chicago and Columbia. They did a lot of sort of proof of concept work, the early experiments to see if this was even feasible. Oak Ridge, Tennessee, they had these enrichment plants for increasing the percentage of uranium-235. Hanford, Washington, they built nuclear reactors there for creating plutonium. Also in Ames, Iowa. Trail, BC, they were working on getting heavy water for the reactors. Chalk River, they built a nuclear reactor. Port Hope, they refined the uranium. And here in Los Alamos, that's where really the center of the scientific effort was. That's where they actually designed and built the bombs. So this project, at its height, employed over 130,000 people and cost $2 billion. Not every scientist who was invited to join the Manhattan Project was interested in working on a bomb. But among those who did were many of the greatest scientists, greatest physicists of that time. The scientific director of the project, the so-called father of the atomic bomb, was J. Robert Oppenheimer. I'm going to show you a clip of some of the other Manhattan Project scientists talking about Oppenheimer. This clip and others that I will show you are from a documentary called The Day After Trinity. It was made in 1980 by John Ells. And I really encourage anyone who's interested in this to have a look at it. That is quite amazing.
Something that might have taken me months to learn before, he would go over in minutes.
Robert Wilson, physicist.
Very fast clip and very elegant manner.
He knew and understood everything that went on in the laboratory, whether it was chemistry or theoretical physics or machine shop. He could keep it all in his head and coordinate it. It was clear, also at Los Alamos, that he was intellectually superior to us.
Somehow Oppenheimer put this thing together. He was the conductor of the orchestra or whatever it was. Somehow he created this fantastic esprit. No matter who you talk to, they all lived it, and they all, I think, almost without exception, felt it most strongly that without him this wouldn't have happened, it couldn't have happened.
If you were in a large hall and you saw several groups of people, the largest group would be hovering around Oppenheimer. He was great at a party, and women simply loved him and still do.
So you might ask yourself, why did Oppenheimer do it? Why did he decide to work on the bomb? Oops.
So I suppose that
Freeman Dyson, physicist.
he was at that time profoundly impressed with the precariousness of the Allied situation, that after all, most of his friends were Europeans, many of them in countries which had been occupied by the Germans. The Germans looked as though they were the wave of the future at that time.
He said there's the danger that this may mean the end of Western civilization.
My brother viewed it as not just something persecuting our own relatives, but as a kind of thing that could be a wave that would walk over the United States as well.
He wanted to help. He thought probably the best way to do this, where he had most competence, would be in the atomic bomb work. And therefore it was natural for him, almost necessary for him, that this is where he would put his effort. He built the atomic bomb, or he didn't build it, but he lent the effort to build the atomic bomb because he thought this was necessary to save Western civilization.
So it's very tempting, very human to make Oppenheimer the face of the Manhattan Project, but there were many, many other scientists working on it, and I think it's useful to consider some of their experiences as well.
I was caught up in the war effort and with it patriotic fever that's hard to imagine nowadays. It's been so long since anything of that kind has motivated America, seems to have motivated Americans, and one would have done anything that was necessary to get on with the war. Yes, it was a good time. It was a good time in America. It was a good time to be American. It was a time when the whole country was pulling together in a cause which even now I think was just. That is, the idea that the Nazis would, Nazi Germany would win that war could have led to, it seemed to me, 1,000 years of dark ages, and everything that we meant by civilization could have come to an end. That's what it seemed to me was what the fight was about, something pretty close to that. And most Americans felt that, and most Americans were just as hard as they could be.
Now, writer Jonathan Schell says that every country that's developed a nuclear weapon has done so in response to a perceived threat from other countries. And it turns out maybe that's the case for the first nuclear weapons as well. But of course, as the war went on, some things became obvious.
The Nazis had never come close to building an atomic bomb. Germany surrendered. The E-Day. Eisenhower returned triumphant.
I would like to think now that at the time of the German defeat, that I would have stopped, taken stock, thought it all over very carefully, and that I would have walked away from Los Alamos at that time. And in terms of all of everything that I believe in, before and during and after the war, I cannot understand why I did not take that act. On the other hand, it simply was not in the air. I do not know of a single instance of anyone who had made that suggestion or who did leave at the time. There might have been someone that I didn't know, but at the time, it just was not something that was part of our lives. Our life was directed to do one thing. It's as though we had been programmed to do that, and we, as automatons, were doing it.
Amazing how the technology tools trap one. They're so powerful. I was impressed because most of the sort of fervor for developing the bomb came in a kind of anti-fascist fervor against Germany. But when VE Day came along, nobody slowed up one little bit. No one said, well, the main thing, it doesn't matter now. We all kept working, and it wasn't because we understood the significance against Japan. It was because the machinery had caught us in the trap, and we were anxious to get this thing to go.
I think it's important to consider what the scientists' experience was, because, we can maybe discuss this after, but I think it mirrors maybe what's happening now in the people who are justifying nuclear weapons or working with nuclear weapons or supporting them in some way. Anyway, Robert Wilson, the first physicist there, was talking about, he didn't know anyone who left the project after it became obvious that the Nazis were not presenting a nuclear threat. There was one scientist that we know of. His name was Joseph Rotblat, and he left the project. He went on to work with medical uses of radiation. He also was one of the founding members of Pugwash Conferences on Science and World Affairs. In 1995, the Nobel Committee awarded Rotblat and that organization the Nobel Peace Prize for their efforts to diminish the part played by nuclear arms in international politics and in the longer run to eliminate such arms. So it's kind of nice in the story that the one scientist who did leave on moral grounds ended up so well. But many of the scientists had doubts. They put together the Frank Report, which sort of imagined what a world with nuclear weapons would be like. It predicted an arms race and encouraged the government not to use the bomb on people in Japan, but to demonstrate first what a powerful new weapon they had, or to keep the whole thing entirely secret. They were worried that an arms race would result if they didn't do that, which actually is what happened. And Leo Szilard, always in there agitating, trying to get something going, he organized a petition that again asked the government to demonstrate the weapon rather than just using it on Japan in a surprise attack. And about 155 of the scientists signed his petition, and many of them lost their jobs as a result. Even Robert Wilson, despite what he's said so far, had some misgivings.
I organized a small meeting at our building. The title was The Impact of the Gadget on Civilization. Hoppy tried to persuade me not to have it. I don't know quite why, but he certainly did try to dissuade me. On the other hand, I went ahead and did hold a meeting, and perhaps between 30 and 50 people came. Hoppy came too, which added a certain, always added a tone to any meeting. We did discuss whether we should go on or not, and in the context of what was happening in the world. But of course, it was called in the context that perhaps what we were doing was morally wrong. Particularly, Hoppy pointed out that, but it would be well that the world knew about the possibility of an atomic bomb, rather than that it be something that would be kept secret while the United Nations was being formed. On that basis, on that logical basis, we all decided that that was right, and that we ought to go back in the laboratory and work as hard as we could to demonstrate a nuclear weapon before the, so that the United Nations would be set up and the awareness of this horrible thing to come.
This idea that, nuclear weapons could be used to establish a new world order, the United Nations, a different way of doing things. It's interesting. It's quite a shift from just defending yourself against the Nazis, which is sort of how it began. And there always seem to be lofty goals associated with nuclear weapons, stopping the spread of communism. I just think it's interesting the way the larger goal manifests itself, and people concentrated on the possible uses of the weapon rather than what the weapon would actually do when it was detonated. So they completed one plutonium bomb. Well, they ended up making 3 plutonium bombs. They completed one, and because the technology was so new and they weren't sure about it, they wanted to test it. This clip really highlights the uncertainty. I mean, looking back, it's difficult to take that into account. The fact that they really didn't know how it would turn out.
The betting pool cost $1. Edward Teller bet on a blast equal to 45,000 tons of TNT. Oppenheimer bet low, 3,000 tons. And I.I. Robbie put his money on 20 kilotons. Young technicians were horrified to overhear Enrico Fermi taking side bets on the possibility of incinerating the state of New Mexico.
There were actually contingency plans for evacuating the whole state. But the Trinity test was, of course, a success. And the scientists who watched it were the first people ever to observe a nuclear explosion.
And we had prepared ourselves with glass, and when we could hear the countdown, when it went off, we all were looking through the glass, and then we saw what was just a tremendous, overpowering vision of this thing happening, seeing mountains fall beside it, seeing perhaps with some kind of beauty, but awesome is what I would call it, as it slowly developed went up in the air and made the whole desert light up as at noon and appear small. A large desert rimmed by mountains appeared to be a small place. And that was just something that once that had happened, I was a different person from then on.
At the time it went off, it was, I think, absolutely, well, I knew sort of what would happen, but I didn't expect the heat from the flash at 5 miles away to be nearly that intense. And then there was a cloud, sort of the radioactive cloud went, sort of hovered there. And I and Ken had been working on developing escape routes, because if that thing had gone a little bit south, it would fall out on camp, and we would have to get out to the south rather than where the north was. The road was to the north. And so there was this sense of this ominous cloud hanging over us. It was so brilliant purple with all the radioactive glowing. And it just seemed to hang there forever. Of course it didn't. It must have been just a very short time till it went up. It was very terrifying. And the thunder from the blast, it bounced on the rocks and then went, I don't know where else it bounced, but it never seemed to stop. And not like an ordinary echo of thunder, it just kept echoing back and forth, and that you're not going to like that. It was a very scary time when it went off. And God, I can't remember what my brother said, but I can't. But I think we just said it worked. I think that's what we said, both of us. It worked, and nobody knew it was going to work.
You wonder, really, if Truman had a good idea of exactly what would happen if the bomb was used, if he really understood. And that this weapon was not just a big bomb, but something different. Certainly the scientists seem surprised, or not to be prepared in some way for exactly what they'd been working for. So as we know, the atomic bomb was dropped on Hiroshima on August 6, 1945. This was a uranium bomb that they used. It was never tested. They were very sure it would work. And anyway, they didn't have any extra uranium to do a test.
The announcement of Hiroshima, I think I was in the hall right outside my brother's office, and it came over the sort of loudspeaker that went through, it was distributed throughout, that the bomb had been dropped and that it had devastated. So the first reaction was, thank God it wasn't a dud. But before the whole sentence of the broadcast was finished, when suddenly got this horror of all the people that had been killed. And I don't know why, up to then, I don't think I'd really thought of all those flattened people. We had talked often about having a demonstration where there weren't people, maybe on the mainland so that the military would see it, but where there weren't people. And then, but they'd actually dropped it on a place where all those people were, and the image of those people, which came before any pictures of it, really was very awful. But the first thing was, I'm sure, was, thank God it worked.
The first reaction which we had was one of fulfillment. Now it has been done. Now the work that we have been engaged in for so many years has contributed to the war. The second reaction was, of course, one of shock and awe. What have we done? What have we done? And the third reaction, it shouldn't be done again.
You were very depressed. I came back from San Francisco and found you very depressed in opposition to your euphoria when the war, VE Day, when we had that very nice party and you started throwing the garbage cans around. You were very depressed, and we didn't have a party. I think there was a party. I don't even know if we went.
Were you depressed?
Yes.
Oh yes, I remember being just ill.
Just sick.
Sick on the point that I thought it would be, violent. I was so overwhelmed when it happened that thing had happened. Still am.
I'm not actually trying to be an apologist for the Manhattan Project scientists, but I can't help thinking if the smartest people in the world didn't really think about what would happen if the device they were making exploded, maybe other people who are in charge of nuclear weapons are not doing that either. It's an interesting human phenomenon, I suppose. Robert Wilson left nuclear weapons research after the Manhattan Project. And he and Hans Bethe, who's the German man talking, helped to form what became the Federation of American Scientists. And the goal of that organization is to bring technological developments to the public so that the merits and the hazards can be discussed, so that these things aren't only left up to a small group of people. But it is wrong to think that all the scientists felt that way. Some of the scientists on the Manhattan Project were very pleased with what they've done, and they said lots of other scientists were building weapons. They did this too, and no need to feel tall apologetic about it. One of these was Edward Teller. He's also known as the father of the hydrogen bomb. Nuclear weapons research didn't stop at the end of the Second World War. They built a second generation weapon. It's called the thermonuclear bomb, or the hydrogen bomb, also the H bomb. It utilizes fission as the others, but there's also a fusion component to that as well. It's much more powerful than the first generation weapons. The kind of weapons they used in Japan, we call those atomic bombs. And they can explode with the equivalent of 15 kilotons of TNT. Thermonuclear weapons can explode with the equivalent of 15,000 tons of TNT. These weapons are easily 1,000 times more powerful than the ones they used in Hiroshima. There's actually no theoretical limit to how powerful this kind of bomb can be. The first thermonuclear weapon was tested in 1952 on the Pacific island of Alujala. This is a photograph of the island before the test, and this is what was left afterwards. A 2-kilometer crater on the ocean floor. The entire island was obliterated. So, with the increase in power of nuclear weapons today, you could put the equivalent of all the explosives used in the Second World War on one missile with multiple warheads. It's really mind-boggling. This is a snapshot of the number of nuclear weapons in the world today. So these are the countries. I'll read that to you because you probably can't see it. The total is 17,300. It's just an estimate. by the Federation of American Scientists. But that's what they say as of December 2012. The first country here is Russia. They have just 8,500. The United States just under 8,000. The next country is France with 300, then China, the United Kingdom. Pakistan and India have about 100 each. Israel a little bit less than that, and North Korea less than 10. All right, the effects of nuclear weapons. The first one, obviously, is that you could kill a lot of people. I took this from an article in Science magazine in 2007, and it talks about the fatalities as a result, not of, the kind of massive nuclear war that we were expecting during the Cold War. That was, 500 million people dead. This is what would happen if 50 low-yield weapons were used. So 50 weapons like they used in Hiroshima. What would happen? That's, I don't know if it's a more realistic scenario. It's certainly one people are more worried about than the sort of massive US-Russia wars. So here are the countries, and here are the number of millions dead. This was calculated if they went to the areas of densest population, and you can see it's obviously millions. So,
sorry, let me ask. You're asking if those 50 were used first on Argentina,
yes,
and then if the 50 were used on Brazil, etc.
Yes.
Okay.
So if India and Pakistan had a war, and each of them used 50 nuclear weapons on the other, there would be 21 million people killed. Which is a lot of people to kill. So, it just brings to the fore this idea that, these countries here that don't have very many weapons and they're not very powerful, still a significant threat.
That's the immediate deaths.
That's the immediate deaths, yes it is. There would be more following as a result. It's worth noting that there is no defense against a nuclear weapon. You just hope you can convince people not to use them. There's nothing, no technical means of preventing the use of one of these weapons. I want to talk about radioactive fallout, and this is something that would affect not only the countries that are targeted, but all the countries. Actually, all of us would be affected, even if we were, survived the attack or were far away from it at the time. So you remember from when I was talking about Hahn and Meitner, the uranium is split in the fission reaction into krypton and barium. Well, it doesn't have to split that way. There are many other products it can form, and then some of these will be radioactive, and so they will decay to form other products that could be radioactive. So in total, there are 200 different products of fission, many of them much more radioactive than the starting materials. So as a result of nuclear weapons use and nuclear power, the whole isotope population of the globe has changed. There is increased amounts of isotopes that didn't exist before the nuclear age. And of course, you can't say that definitively there's been any negative effect of this. We have background radiation on the Earth as well, and the levels of these new radioactive isotopes from fallout, they aren't that high at the moment, but we know that in areas that have been subjected to large amounts of radioactive fallout, the effects are devastating. America did a lot of nuclear testing here in the Marshall Islands. Most of the tests were done on these two islands and then Then the radioactive fallout blew onto these islands here. Draw your attention to this island, Rongelap. They saw increased rates of cancer and birth defects as a result of the testing. This woman, Lejean Nalang, she's from the Marshall Islands, and she testified about the effects of the fallout. These are her words. The most common birth defects on Rongelap and nearby islands have been jellyfish babies. These babies are born with no bones in their bodies and with transparent skin. We can see their brains and hearts beating. Babies usually live for a day or two before they stop breathing. So, apparently these children are still being born today. And keep in mind that's 3 generations, or 2 generations away from the people who were actually exposed. The nuclear testing there stopped in the late 50s. The next photograph I'm going to show you is of a child with birth defects from the Marshall Islands. It's not a jellyfish baby. This baby will probably live for 6 months. She was never, she wasn't alive when they were doing the testing. Her parents weren't alive when they were doing the testing. It was her grandparents who were alive and who were exposed when the fallout fell. So, this intergenerational effect is one of the consequences of nuclear weapons use that we really have to take on board. There's another effect called nuclear winter. It has not been observed, it has not occurred, but it's predicted. When a nuclear weapon explodes, it creates a tremendous amount of heat. This is a photograph of the Trinity test, 16 1,000ths of a second after detonation. This is a fireball. It's 200 meters across and it's as hot as the sun. Every plant and animal inside that was instantly vaporized, and the sand underneath was melted into glass. So you can imagine, this is the desert. But if many bombs like that were dropped in urban areas where there's a lot of flammable material, it would start tremendous firestorms. And the huge number of firestorms would create tons and tons of soot and debris, which would rise with the heat into the stratosphere above the level where it could be rained down, and then it would block out the sun. I'm just going to show you, it's a simulation that shows you how the smoke would spread with a full explanation.
A nuclear war between India and Pakistan would produce fires in the cities. The smoke generated would be locked into the atmosphere and blown around the world as shown in this movie. It would block out so much sunlight that it would get cold and dark at the Earth's surface, plunging us into temperatures colder than the Little Ice Age immediately. This would be climate change unprecedented in recorded human history. For more information,
it's worth keeping that in mind. The nuclear war between India and Pakistan, and we're just using them because they're convenient examples, that's going to affect us here. Obviously, if it gets cold and dark, we'll have difficulty growing food. This is a map of the Canadian prairies. This is where we grow wheat at the moment. If there was an average 1 degree drop in temperature, we'd only be able to grow wheat here. And if the temperature dropped by 2 degrees, and that's the kind of temperature drop they're predicting from a small nuclear war, we'd only be able to grow wheat in southern Manitoba. Obviously, there are lots of other effects of nuclear weapons. And I'm not going to go over everything, but the International Court of Justice has listened to evidence about nuclear weapons. This is the court associated with the United Nations, and they were asked to give an opinion on the legality of nuclear weapons. So they listened to all the testimony about the effects of the weapons. And these were judges from a variety of countries, many of them countries that possess nuclear weapons. And they unanimously agreed on this statement, among other things. Only nuclear weapons have the potential to destroy all civilization and the entire ecosystem of the planet. So I hope there'll be some discussion. Just to end with this quote from Albert Einstein, which you're probably all aware of. The unleashed power of the atom has changed everything save our modes of thinking, and thus we drift towards unparalleled